Here we go, mark your own. Have to do my favorite student, good old Ann. I don't know if I told you the other day on my YouTube channel, I got a comment on one of my videos from a student. Who the heck is Ann? Oh, okay, they didn't get the joke. One of the questions that students ask is, Mr. Duke, okay, when do I use conservation of momentum? When do I use just plain old impulse? Conservation of momentum, more than one object. I looked at number one, it's a collision, it's more than one object, that's going to be the law of conservation of momentum. So it says this, the fact that I see north and I see south, that's a bit of an alarm bell, Geo. I spotted that ahead of time. I'm going to let north be positive. I'm going to let south be negative. And since this was south, that's also going to be negative. Okay. There is a collision. The sum of all the momentum beforehand equals the sum of all the momentum after. Before the collision, oh, you know what? I'll call this mass A. I'll call this guy mass B. Sorry, let's put the A above the 72 so I know that's the number it's associated with so I don't get confused. Before the collision, what's moving? Well, it's going to be mass A, velocity A initial, and mass B, velocity B initial. They're both moving separate. Wham! They collide. After the collision, what's moving? Mass A, mass B, both or neither? I think both and separate. What kind of a collision is this? Elastic or inelastic? Because I'm going to ask you that question on the test. Elastic, rubber band, bounce apart. They bounced apart, elastic, rubber band. So I'm going to have M, A, V, A final plus M, B, V, B final. And it looks like they want the final velocity of the second player. I think I'm going to minus this over to that side and then divide by the mass of B. I'm going to get the mass of A, velocity of A initial, plus the mass of B, velocity of B initial, minus the mass of A, velocity of A final, all divided by the mass of B. That's going to give me the velocity of hockey player B after the collision. And now I can plug and chug carefully, but okay. Mass A, 72. Velocity A, positive 7.5, plus sign. Mass B, 65. Velocity B, negative 8.1, minus mass A, 72. Velocity A final, negative 1.3. All over 65. These two are having a head-on collision. Yes? Alec, what's the mass of the first hockey player?
72.
Really close to 70. What's the mass of the second hockey player?
65.
Really close to 70. They have roughly the same mass, roughly. What's the speed, not the velocity, just the speed of the first player? 7 point.
5.
What's the speed of the second guy?
8.
Also really close. You know what? They have roughly the same momentum. I'm going to bet that we get a really small answer. I'm going to bet when they collide, their momentums almost cancel out. In other words, if I get a velocity of like 17 meters per second, I don't think so. These are almost identical momentums, but in opposite directions. I think it should be a really, really small answer. Let's find out. Is it?
Yeah.
Like I'm going to guess less than 3. Yeah, okay. So I have a bit of a gut instinct just because I glanced at the numbers, kind of what I should be heading towards. Oh, minus Mr. Duke, plus 65 times negative 8.1, minus 72 times negative 1.3, brackets around the top, divided by 65. 1.64? 1.65, sorry, is that right? And positive, so north?
Yep.
Yes? Okay. So final answer for full marks. V final equals 1.65 meters per second. North. For you to get full marks, I would expect the direction and the units. Zach, I would expect the units as well. I'm not sure that you had the units on yours when you handed it in. I might be mistaken. Oh, you did. Good. If you did not get that, so that would give you 3 out of 3. Otherwise, what would I do? 1, 2, 3, 4. Yeah, I'd probably go something like this. Half mark if I saw that. 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 And then a half mark for the velocity, sorry, speed, and a half mark for the direction that gives you the velocity. Something like that. But again, if you get the right answer and you took some shortcuts, 3 out of 3. If you missed this negative right here, or you missed this negative right here, but you plugged everything in right, you just missed the direction, probably I'd give you 1.5 out of 3, because to me, I really want to emphasize direction. Momentum is a vector. We got to pay attention to direction. Speaking of changes in direction, that's going to be important. Upwards, I'm going to let up be positive. I'm going to let down be negative, because that is a change in direction. I also noticed geograms. Okay, they want the impulse. Well, impulse is change in momentum, and it says I can calculate that by going force times, I don't see a force. I do see a time. I do notice that part B wants me to find a force, so I think I'll use that later. I'm going to use impulse equals, now the formula sheet says that, except what does a delta stand for? A triangle. Change in, and what's change in anything? So really, I was lazy on your formula sheet. It's really MV final minus MV initial. The mass is 52 grams, which is going to be 0.052. The final velocity is 6.2 minus. The mass is still 0.052. The initial velocity is negative 8.2. By the way, you could have let down be positive and up be negative. I'll give you full marks just as long as you're consistent in your directions. Typically up and down, because of free fall, my habit is up positive, down negative, because that's what we did in free fall, and I'm worried if I flipped it, I'd mess up partway through and lose track. So that's me being paranoid. 0.052 times 6.2 minus 0.052 times negative 8.2. There we go. You get 0.7488, 0.75, 0.749. I'll go 0.75. That's the magnitude. Units, well, kilogram meters per second, because it's momentum, change in momentum. Direction, up. Up. I would give you half mark for that, half mark for that, half mark for the magnitude, and a half mark for the direction. If you missed the negative, you would have. If you missed the negative, you would have gotten negative 0.104, which would have been down. I'll give you 1 out of 2 if you got that, but I'll only give you half marks if you missed the directional change. What's the average force? Oh, now I think I can go impulse also equals force times time. I think now I can say force equals impulse divided by time, which is going to be 0.7488 divided by 0.15. You get 4.99. If you rounded it to 5.0, I'd take that. Units, it's a force. Direction. Did I get a positive or a negative answer?
Positive.
Which was?
Upwards.
Up. Oh yeah, the floor does apply an upwards force. Trust me, do a belly flop on the floor and you'll find it applies an upwards force. I would give you half mark for that, half mark for that, half mark for the magnitude, and a half mark for the direction. But again, Jay, if you got it right, 2 out of 2. Number 3, turn the page. Car has a mass of 1,200 kilograms. This car changes velocity from that to that during an calculate the magnitude of the average force. I think this time I'm going to combine both steps from the previous question. I'm going to start out by saying impulse equals impulse. I think in this case, they want me to get the force by itself. By the way, I would also have no problem on your test, Ange, giving you the force and the time, giving you one of the velocities and saying, find the other one, find the initial velocity or find the final velocity. Also, you can still do all of this using kinematics, and I'll show you a way to do that in just a second, using all stuff before we knew momentum. You can do it the long way. But for now, what I like about this is I already got the F by itself pretty quick. I'm going to divide by delta t. It's going to be m v final minus m v initial divided by the change in time. Since time is a change, always a change, and we get sloppy often and we drop the delta. So the force is going to be m 1200 v final 25 minus 1200 times 12 divided by 8. This might work out almost evenly. 1200 times 25 minus 1200 times 12, close bracket, divided by 8. Is 1950, right? Units, it's a force. Direction, didn't ask for it. That's why I used the word magnitude. I said find the magnitude of the average force. I don't care about direction this time. Did anybody do it the previous way using F equals ma and Vf equals Vi plus At? Okay. Did you get the right answer? Okay. Sorry? No, I'm looking next to you. Yeah. Okay. Then 2 out of 2 for that too. I'm not going to bother doing it since you're the only one. You're just not worth. Never mind. Number 4. Oh, and I guess same as before. What would I do here? I would probably go, honestly, 1 whole mark for that, half mark for that, and then a half mark for the answer, because there's no change in direction here. I wouldn't be as fussy at plugging in the numbers. Oh, number 4, they want me to find change in velocity. I'm going to do exactly what I just did for number 3. I'm going to go impulse equals impulse, but this time, instead of breaking the change in velocity down into final minus initial, I'll say, okay, they want the change in velocity. It's that thing. Jason, how would I get the delta V by itself? How would I move the M over? So you're telling me if I want to find the change in velocity, it's going to be force change in time divided by M. You would be correct, sir. By the way, little nerd moment, don't write this down. What if I divided by delta t? I would have this. Delta V, don't write this down, over delta t equals F over M. What's force divided by mass? If you get F, huh? And at the very beginning of the year, I also told you acceleration was the change in velocity over time. Remember, this is Vf minus Vi over t equals A. That's also where that Vf equals Vi plus At equation comes from. It all comes from this combined impulse equation. It's really several equations in one shortcut. Handy. Nerdish. 120 times 8 divided by 40. Oh, I should be able to do this in my head. There's going to be a 24? Now, this doesn't mean that V final is 24 meters per second. That's the change in velocity. If we started out at rest, V final is 24 meters per second. If we started out at 5 meters per second, V final would be 29 meters per second. We could even have started out going backwards and ended up going forwards. 0.5, 0.5, 0.5, 0.5. Number 5, did anybody spot the problem with number 5? Because I caught it and I've changed it on my original, but you guys will be the last ones to spot the problem. Maybe there isn't a problem. I think there is. Let's find out. This is a collision. This is a job for conservation of momentum. The sum of all the momentum beforehand equals the sum of all the momentum after. You know what? I'm going to use G for George and J for Jim. You can use A and B, but I'll use G and J. They got letters there. Before the collision, both are... Oh, wait a minute. I see east and west. I'm going to let east be positive. I'm going to let west be negative. So this number here is going to be positive. This number here is going to be negative. This number here is going to be positive. Okay. Mass of George, velocity of George initial, plus mass of Jim, velocity of Jim initial. Wham! They collide. After the collision, we're going to have stuck together or separate? Separate, both moving. Mass of George, velocity of George final, plus mass of Jim, velocity of Jim final. This is really similar to question number 1 in some ways, in that we have 4 different momentums, 2 on the left, 2 on the right. And it's going to be a similar mathematical process. I think I'm going to minus this over and then divide by the mass of Jim. I think I'm going to get this. Mass of George, velocity of George initial, plus mass of Jim, velocity of Jim initial, minus mass of George, velocity of George final, all divided by mass of Jim. That's going to give me final velocity of Jim. Here we go. Mass of George, 65. Initial velocity of George, positive 12. Plus mass of Jim, 85. Initial velocity of Jim, negative 7. Minus mass of George, 65. Initial velocity of George, positive 4, or sorry, final velocity of George, positive 4, all divided by 85. Is that right, folks? Pull up my trusty calculator. 65 times 12 plus 85 times negative 7 minus 65 times 4 divided by 85. Do you get negative 0.88? What direction would that be? Negative? I let east be positive. I let west be negative. So if I got a negative, what direction am I getting? Okay, so I'm going to say V final is 0.88 meters per second west.
Oh, I put negative 0. I put negative 88.
I'd give you 2.5 out of 3. Half mark, half mark, half mark, half mark, half mark, half mark. I think that adds to 3. Before you put this away, first of all, what's the problem with this question? Why is this question garbage? Okay, look up. Here's the 2 hockey players, yes? They collide and go like this. They somehow went through each other, didn't they? So I fixed that. If you flunk my course, next year you'll find actually they bounce off each other properly. I made sure of that. Yeah? But then they wouldn't be going east or west, they'd be going at angles. True. Which, by the way, is a great segue into Physics 12. In Physics 12, we ask just that question, and we get triggy with it like you wouldn't believe. It's a lot of trig, but it lets us handle non-head-on collisions. You can have broadsides, or you can have glancing collisions as well. They're called oblique collisions, which is a fancy schmancy word. Speaking of fancy schmancy, can you give yourself a total score out of 14 on the very, very top? Lesson 1 work, our next unit. So I'm not quite going to get to be able to give you a test on this. I will put some of this on your final, not a bunch.
And I will try and give you a practice take-home quiz so you have an idea of the kind of questions we're going to ask. We want to talk, did I count right? Okay, just leave it there. I'll get it in a second. In physics, the word work has a specific meaning, and unfortunately in English, it means something different. In English, when you say, I'm doing work, you mean, I'm getting tired. I don't have as much energy. I'm getting tired. In physics, work is not tiredness. We will talk about what tiredness is in physics, power, in case you're wondering. Instead, work is done on an object. You don't do work, you do work on something else. If work is to be done on an object, there are two things that have to happen. Number one, a force must act on the object. And number two, the object must move through a distance in the same direction as the force. Work is a scalar. It has no direction. And it's calculated by, so the symbol for work is a capital W. Yay! None of this P for momentum, W for work. And it's force times distance. It's on your green sheet somewhere there. Although I probably just wrote FD, I probably didn't put a time symbol between it. Should be about 2/3 of the way down, I think, Ange, I think. Yes, there it is. What are the units for work? What are the units for force? Times. What are the units for distance? So it's technically a Newton meter, except work is such an important concept, we've given it its own unit. A Newton meter is now a capital J, a joule. Work is measured in joules, named after a scientist whose last name was Joule. Okay? This equation only works if the force is constant. If you're going to have a changing force, we're going to have to come up with something else. But Gracie, we're going to start out here by defining work as applying a force and moving an object a distance. You've done work on that object. Question number one. How much work does it take to lift a 12-kilogram mass from the ground to a height of 9.5 meters? Jenny, put that up. Geo, what does example one want me to find? How much what? It's in front of you in your notes too. Example one, how much what? Yeah, there you go. So here's our new equation. Ready? Write this down. Work equals force times distance. All of you right now, could you please underline the word lift? When you lift something, which force are you doing work against? So now, put a little G right there, a little FG. What was the equation for FG? Get the obvious one. What did we write? Yep. There's the force times the distance. Now, typically when we're talking about a vertical distance, it's traditional in physics to use an H for height. So often if you're asking me, when you're lifting something, how much work are you doing? It's MGH. But can you see, Alec, it comes from force times distance. There's the force, there's the distance. But if you skip that force times distance and you go straight to say, that's MGH, I'm fine with that. In fact, we're going to do that eventually. What's the mass, Alec?
12.
What's G? We all know this by now. We've memorized it. 9.8, and not negative because work is a scalar. Okay, we don't care about direction here. So 9.8. And Alec, what's the height?
9.5.
How many joules of work would it take to lift this object up?
1,117.
1,117.2. I'm going to go so what was it? 1,000?
111.
I'll go 1120. I'll go to 3 sig figs. Really, I should go to 2 sig figs, but there. What is that telling me? It's also telling me how much energy it would require to lift that object that high. What is that telling me? It's also telling me that that object has gained that much energy and something else has lost that much energy to get it that high. Work tells us a lot of things, and we're going to get into that into more detail. Cody pushes against a brick wall as hard as he can for 12 seconds. So I'll be Cody. Here's the brick wall. If I push against the wall as hard as I can, will I get tired if I keep pushing and pushing and pushing? Yes. Am I doing work?
Yes. No.
Why? Am I applying a force? Yes. Is the wall moving a distance?
No.
This is what I need to lovingly get out of your heads. Work is not fatigue. Work is not tiredness. Work is very specific. You're applying a force over a distance. So how much work has he done? None. Since D equals 0. Okay. Suppose you're pushing a box along a floor, you're sliding it, and it requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? Is there a force? Yep, 22.5. Is there a distance? Yep. Now pause. Are the force and the distance in the same direction? Because that was the other thing I said at the very beginning. They are. What do you get?
306.
306? Really? Works out nice? Look at that. 306 what? Joules. But the force and the distance have to be in the same direction. Let me give you an example. Pause the video. This notion that the force and the distance have to be in the same direction actually is a great time saver, is really, really handy. Dylan pedals his bike up a 19-meter high hill that is 91.4 meters long. The combined mass of the bike and rider is 65 kilograms. The bike requires a steady force to continue up the hill. If the hill is at a 12-degree angle, how much work does Dylan do? This looks terribly tough and terribly confusing. It's not. First of all, let's write down work equals force times distance. When you go up a hill, which force are you actually doing work against? Why is it tough to ride up a hill? Gravity. So riding up a hill is going to be the force of gravity times distance. What was the equation for the force of gravity? Get the obvious one. mg. What direction is gravity in? It's vertical, so I'm going to use a height. I don't need to worry about that 91.4 because that's not in the direction of the force that I'm doing work against. I don't need to worry about that 12 degrees or what. I don't even need to know how hard I have to push up against the hill. That's not what this question is asking. This question is saying how much work, how much energy will it take to get to the top of the hill? It's going to take 65 kilograms times 9.8 times the height of the hill. That's all we care about because it's a scalar. And I get 12,100 joules of work. Is that right? Yes? If Dylan was riding this bike, he would burn through 12,100 joules of sugar energy, of calories. And the beauty about work being a scalar is it doesn't care about the pathway you take to get there. If this hill had gone like this, look up. If the hill had been really steep at first and then gotten shallower and then gotten steep, same amount of work. Doesn't matter. You're doing work against gravity and the height that you ended up at hasn't changed. If the hill had been really strange, really steep and then gone down, same amount of work, because you ended up right there. You did 19 meters of height against an mg of gravity, which means work is going to be really, really handy for analyzing stuff that looks like that from the side, like coasters. Yeah. To try and analyze something like a roller coaster with a vector method, which would have to take into account every little change in direction of the hill, ugh. But with a scalar approach, no problem. This is one of the nice characteristics about work. It's a scalar. How much work would it take for Dylan to ride to the top of this hill? I don't care about the path. I don't care, even if he started going down and then ended up going up. All I care about is where he starts and where he ends, and the fact that he's doing work against gravity. Work is going to be force times distance. If you're doing work against gravity, it's going to be mgh. I've scrolled down. What was Dylan's mass? G is 9.8 times 24. 15,300 joules of work. Mr. Duick, how can that, no pun intended, work? How can that be the same as just going in a nice straight line? He loses energy here, going downhill, he gains some energy back, loses, gain, it all works out. What takes more work? Lifting a 25 kilogram mass to a height of 4 meters, or lifting a 50 kilogram sack to a height of 2 meters? Okay. In other words, the amount of energy required to lift something that's lighter further up is the same as the amount of energy required to lift something that's heavier but not as far, which makes sense. Work is what times what? Force times distance. Work is what times what? Now the force and the distance have to be in the same direction. Okay. What if the force is not constant? Because I told you that equation only worked if it was constant. What if the force is changing? Well, work is also the area under a force versus displacement or distance graph. Here is a graph. On the y-axis is force. On the x-axis is displacement. And I notice the force is changing because the force is getting higher. So I couldn't just go force times distance. Elliot, what does this question want me to find? More specific. Keep reading. Moving the object from?
2 meters to 5 meters.
Okay, we want to find the work moving it from here to there. I can't go force times distance. I can't go 8 times 5. And the reason is, look, the force is changing. It's getting steeper. It's changing. So whenever they say how much work, my first thought is force times distance. But if that doesn't work, my second thought is, Elliot, can you read me this?
Work is also the area under a force versus displacement graph.
It's going to be that area. What shape is that? What do you call 2 parallel sides and 2 non-parallel sides? Begins with the letter T. It's a trapezoid. For a candy, does anybody know the equation for the area of a trapezoid? Because there is one. Okay. There's a reason why none of you do. It's cool, but it's totally redundant. It's unnecessary. It's a nice shortcut, but you don't need it. And the reason you don't need it is any trapezoid on Earth can always be broken up into a triangle and a rectangle. And those ones you've done. What's the area of a rectangle? Length times?
Length times width.
Yeah. What's the area of a triangle? Base times height divided by? I think I even put those on your green sheet. I can't remember. So let's be a bit organized, but let's also be lazy. So here's how I do these. I'll call this area Roman numeral 1. I'll call this area Roman numeral 2. I will draw the line so I can see what I'm... Did I put them on there or not? No? Okay. I gave you Pythagoras? Really? Wow. So area 1 is going to be base times height divided by 2, because it's a triangle. What's the base of that triangle? Look at the graph and look at the numbers and figure it out. How long is the base? 3, right? From 2 to 5? What's the height of that triangle? Don't say 8, because it's not.
6.
Right? Goes from 2 to 8?
6 divided by 2.
I guess it's 18 divided by 2, which is?
9.
Or is that a German student saying? No, okay, 9. The second area is a rectangle, and that's length times width. What's the area of that there rectangle there? What's the length?
3.
What's the width? I think 2? Is that okay? 2 times 3, 3 times 2 is?
6.
You know what? I don't need a calculator.
How much work was done? I don't even know, and here's the beauty. I don't even know what the object is. I don't know its mass. I don't know how big it is, but I can tell you how much energy was required to move it from 2 meters to 5 meters. How much? How many joules of work? So we have 2 definitions for work. Work equals force times distance, but this requires a constant force. Or work equals the area under a force versus distance or displacement graph. How do I know which one to use? I'll give you a hint. If the question gives you a graph, it's probably that one. If the question doesn't give you a graph, probably the force is constant. I mean, that's not in real life, but in terms of what I'm going to be throwing at you, sure. We're going to pick up with this Wednesday, and I'm also going to try very hard to get through lesson 2 on Wednesday. Your test is Monday. Your homework is to work on the study guide. For the remainder,